It's really just a thrill to be speaking at a conference in honor of Howard Stein. I don't have personal experience with detailed interactions with Stein, but like a lot of you here, his work has really influenced my own. And my title is meant to partially acknowledge my debt to Stein. This is a paper that hasn't been mentioned yet. There's a 1994 paper by Howard that's titled Some Reflections on the Structure of Our Knowledge in Physics. And I'm really influenced by that paper in particular in the talk I'm giving today. So let me start by acknowledging there's a kind of ambiguity in the phrase structure of knowledge. And this is something Howard points out as well. There's kind of three different aspects of the structure of our knowledge. The first is knowledge as a positive achievement, a systematically related set of claims about a given domain. And I follow Howard in thinking that, there are people who wonder whether we have knowledge in physics, and I think there's no point in responding to them in detail. But there are, so I'm going to be looking at cases of claims about knowledge in cosmology in particular, rather than physics in general. So a second claim about the structure of knowledge, or a sense of the structure of knowledge, is a structure that's the kind of thing that we can have justification or evidential defense for. So how is it that those claims are related to the evidence available to us? And finally, there's a prospective sense. How can current knowledge form a basis or a framework for further inquiry that can lead to progress in developing more positive knowledge and also stronger evidence in support of those claims? And that's really probably the main theme I'm going to focus on today. So Howard turns in the 1994 paper and a lot of other work to looking at Newton's innovative methodology in the Principia as the touchstone for considerations of the structure of knowledge. And he looks at Newton's work and the subsequent development of celestial mechanics in order to consider how to characterize the structure of our knowledge in physics. My focus will be in physical cosmology, and in particular how it's been pursued in the last century since Einstein first formulated the field equations for a model of the universe as a whole, and asking how evidence has developed in this area, in a very sketchy way, obviously. But as what will be clear in what follows, Howard's work on Newton has really informed the way I'm approaching this task, as has the work of my colleague Bill Harper and George Smith, in thinking about how we've gathered and developed evidence in this domain. So one of the themes of Howard's paper is a question of how to characterize the empirical content of a theory. Or as he puts it, how should we get the laboratory inside the theory in the sense of clarifying what a given theory is as a theory of a mathematical structure discernible in the world of phenomena, of observations, or of experience. And so Howard's main focus in the discussion is contrasting a view of Carnap's with a view that he's proposing. And at the risk of really dramatically oversimplifying, his proposal is that connecting theory and observation requires schematically representing an observer within a theory. So the end goal isn't some kind of deduction of observation, which would be a claim about the experience of an observer in a particular setting. That's not something that he thinks is even feasible. Rather, the point is to give an account of how an observer, represented very schematically, as a part of the physical system described by the theory, can objectively measure physical quantities that are postulated by the theory. And the results of the measurements then, in some sense, could provide the sensory material on which the imagination and so on, the thought of the observer could work, but it's not meant to actually deduce a straightforward observation claim. Such an account will be schematic in the sense that it provides a very idealized and partial representation of an observer or an experimental situation. But there's a crucial aspect of the account which draws upon the resources of the theory. Namely, in what context can we actually be said to be reliably measuring the fundamental quantities that the theory has introduced, such as mass in Newtonian mechanics, or spatial geometry, length in the case of special relativity. So this is something that comes up in the paper that Ollie was discussing this morning, the 1991 paper. He has a discussion of what it means to attribute Minkowski geometry and how we could think about measuring Minkowski geometry in detail. So while the relevant theory will generally not give a full account of how a measurement proceeds, it will rely on a number of other theories, so giving a really full account of any particular observation or experiment will not draw on a single theory. But the theory in question, so the theory introducing the concept of mass or the theory introducing length, will be an essential part of that account of measurement in order to be able to support the claim that you've reliably measured a quantity. Now, so in the case of cosmology, there's a long tradition of people voicing skepticism about whether it's possible to have knowledge in cosmology. And so that makes the question of the structure of our knowledge in cosmology perhaps seem more pressing than in other areas of physics. So this is a passage that comes at the end of Roberto Turretti's excellent historical and philosophical discussion of the early days of relativistic cosmology, but it ends on a very skeptical note. And so let me mention a few of the grounds Turretti has for, as he says, thinking that we shouldn't think of the standard model of cosmology as an unmitigated success. He wants to throw some cold water on that idea. So the first thing he mentions is the universe as a whole cannot be considered as a scientific object in any sense that such words have had in the historical development of physics. There he's quoting Powery. I mention this, but I really want to set it aside. It's a question that a lot of people in cosmology as well as philosophy have focused on, that cosmology is somehow a theory of the whole universe, and that there's obstacles to formulating modalities in that kind of context because the universe is unique and you don't have multiple instances and so on. I think there's some interesting questions there, but I think most of cosmology should instead be regarded as descriptions of the large-scale degrees of freedom of the gravitational field or other aspects of physics. And so I think the threat of uniqueness is not actually particularly relevant for most areas of cosmology. And I'm not going to be talking about the early universe or theories of origins today, so I think this question is actually not really one that is a particular threat to the knowledge that we have of the standard model. So, but Turretti goes on to mention a few other sources of skepticism about our possible knowledge in cosmology. One is that, for example, he thinks that the description of the cosmic background radiation, which is a source of information about the early universe, requires a combination of quantum mechanics and general relativity. He thinks that since we don't have a theory integrating those two, somehow that casts suspicion on the use of the background radiation. I think that's a weak argument, so I'm going to set that aside. I think the most interesting question is this last one, and that's going to be related to things I'll be discussing further, namely, how do we reconcile the very symmetric space-time geometry that is used in the standard model of cosmology with the fact that the actual universe on local scales, at least, is lumpy. Right? So how do we think of then gathering evidence about the overall standard model, this sort of very symmetric description, and how do we reconcile that with the lumpy actual universe? So that's, I think, something that is a more interesting kind of question about how the idealizations that we've built into our theory are actually handled. And so rather than focusing on these general sources of skepticism, what I'm going to be focusing on today are what I'll call generally evidential challenges. So as in most areas of physics, in cosmology, the reasoning that we employ is heavily theory dependent. So theory is essential in allowing us to extend our epistemic reach, to use observations or features of the universe that we see in our telescopes to make claims about the distant history of the universe or the overall space-time geometry. And there's natural worry that because of that kind of theory dependence of the reasoning, that there might be a threat of circularity here, that the theory will somehow be immune to further testing because all of the ways of understanding measurements are in fact based on theory. But I think one thing that's important, and I think this is one of the themes of Stein's paper, is that you shouldn't think of theory dependence as immediately leading to vicious circularity. In fact, we use theories throughout physics. There's a famous passage from Laplace where he says, and George will correct me if I get this wrong, that the Newtonian gravitational theory was just as important an instrument in the development of celestial mechanics as the telescope. And so, in that sense, theories are used instrumentally in a way that is essential to developing further evidence, and it isn't automatically something that leads to a kind of vicious circularity. Another question, which has become more important in contemporary cosmology just because of the level of precision that's been reached in the measurements that are being performed now, is to understand the kinds of idealizations that are employed in describing measurements. And a further question then is, what more can we learn by further controlling and understanding these idealizations so that we can both assess the reliability of the measurements, whether they're sensitive to features of the idealizations, and also whether we can learn things because of discrepancies with what we expect. That if we have control over the idealizations, then the discrepancies will be more meaningful than if they just than if we just have approximations which we don't understand this data set. This is another theme that George has emphasized in looking at the development of Newtonian physics in particular. So these are the two themes that I think are interesting questions about the status of contemporary cosmology, and that's what I'll be pursuing in a very partial way today. So I'll first, a lot of you won't need this, and it will be a quick tour of the standard model of cosmology. Very briefly, I'll mention a few things. Then I'll come back to look at this second point that Toretti raised about how to think of the actual universe in relation to the very symmetric descriptions of space-time geometry that are part of the standard FLRW models. And then I'm going to be looking at two specific issues. There's a danger here in the sense that I don't think either of these are things that there's a consensus that's been reached in the scientific community yet. They're, in some sense, aspects of the fitting problem in relation to very specific claims in contemporary cosmology. I'm using them to illustrate the importance of thinking through what's going on in measurements and the nature of the measurements that are being performed. Although I think that in both cases there's open questions about whether we have to worry about the inhomogeneities in describing light propagation in the way that some people have started to model, and whether the local small-scale inhomogeneities will lead to an important amount of back reaction. So I'll describe these. I think for my purpose, the more important point is that they illustrate a kind of methodological approach of trying to understand the idealizations we're employing in a much more detailed way that's being forced on us by the level of precision cosmology has reached. And I think they can illustrate that even if the jury is still out on the conclusions we can reach. Okay. So first let me say something very briefly about the standard model of cosmology. So one part of the standard model is that it's based on extrapolating local physics to enormously larger scales than where it's been tested. So for general relativity has been subject to precision tests very roughly on small scales down to millimeter scales, and up to scales that are larger than the Earth's orbit, so solar system scales. And this is the results of a project that was carried out starting in the 60s, of very carefully delimiting the space of possible theories that would be modifications of, or sort of possible gravitational theories of which general relativity is one, satisfying sort of general principles that in effect mean that they're metric theories, so they're similar in some ways. It's a very conscious effort at a limit of induction that allows you to take all of these solar system tests and put tight bounds on what the parameters are such that the theory that's preferred by all of these tests is very, very close to general relativity. So this is the result of the efforts at a decades-long effort of constraining the gravitational theory based on solar system tests. And more recently, there's now a number of strong field tests. So looking at the LIGO results, which I've shown here, which you can't see very well, but there's now 3 reported cases of gravitational waves that have been detected. Those are a different regime that's being tested, strong field regime. And also there are observations of stars near Sagittarius A star, which is or observations near Sagittarius A star, that's the supermassive black hole in the center of our own galaxy, that can also be used to look at the strong field regime. And in extrapolating this to cosmological scales, we're assuming that this well-tested theory of gravity then extrapolates up to apply to the universe as a whole. So that is a substantive claim that the at cosmological scales that the gravitational dynamics we understand still applies. Now, I'm not actually going to be here talking at all about modifications of general relativity. There's been also a lot of exploration of whether you can modify general relativity for its implications in cosmology. I'm not going to be focusing on those today. What I want to focus on is, in parts of the standard model, the predictions actually rely not just on general relativity, but on claiming that the universe is well approximated by a perturbed FLRW model. So the FLRW models are a simple set of models that are homogeneous and isotropic, which have different possible geometries, which are illustrated here. And the Einstein field equations lead to a set of simple differential equations for the scale factor, where R here is the scale factor that characterizes how two nearby observers, how the length between those change over time. Rho is the energy density, P is the pressure, and lambda is the cosmological constant. And so they're a very simple set of models that have been used for describing the large-scale structure of the universe since the 1930s. Then there's also, in order to describe perturbations over in order to describe structure formation, you can introduce perturbations over this geometry. Now let me shift to saying something about the evidence for the standard model of cosmology. So I think this is meant to illustrate the kind of argument that people have given starting from the 1960s, although this is reflecting very recent data. So the cosmological models include a lot more than just the standard geometry of the FLRW models. They include a thermal history that accounts for example, Big Bang nucleosynthesis, a series of nuclear processes that occurred in the early universe. And then there's the surface of last scattering, which is when photons decoupled from the plasma at around 400,000 years after the Big Bang. And the properties, the physical theories ascribed to those epochs can be used to constrain different features of the models in ways that you can then check for consistency of the overall account. So in this case, this is just a pedagogical diagram, so it's not particularly precise. But what you see here is a chart of the different element abundances of the light elements as a function of the matter density at the time when those elements formed. And it also turns out that the precise structure of these peaks of the oscillations that you see in the CMB, the temperature fluctuations in the CMB, also depend upon, it's not just the matter density, but the matter density times the Hubble constant at that time. And so you have very different aspects of the physics. This is in the first 3 minutes, this is 400,000 years after the Big Bang, which are both related to the parameter, namely the density of matter in the early universe. And you have consistent measurements of that density given observations of these two different phenomena. So I think in a lot of cases when you have people, so for example, Jim Peebles, other people, when they make the case for the standard model, it involves a huge extrapolation of known physics to these scales. And that extrapolation leads to an account that has a relatively small number of parameters. There are different ways of writing down the basic parameters that characterize the model. Here's one of them where you have 6 basic parameters. These are derived from those 6. And you can take a variety of measurements and try to determine the values of those parameters. So I just mentioned one that you can, from the primeval element abundances, you can constrain what the density of matter was in at the stage of nucleosynthesis. From the observations of the CMB, you can also determine the matter density. And you can go through a very long list of similar cases where you're using different phenomena to try to constrain this simple set of parameters that characterize the FLRW models. So this is a case that's very much like the kind of case that Perrin gave for atomism, which was mentioned earlier. There's a simple model here with a set of parameters, and it looks like we have independent measures of those parameters because they come from phenomena that have different physical descriptions, and overall it seems that these are consistent measurements. So I will acknowledge the strength of the argument of this type. So think of this as a kind of overdetermination argument for the underlying model. The strength of an argument of this type depends on 3 things, just as is the case with Perrin's argument. First is just the level of agreement and the precision of the measurements. So, and as I'll discuss below, there are some discrepancies in the cosmological measurements that are interesting and might tell us more about the universe. Second, to what extent have we established that we actually have a clear connection between what we're observing and the quantity that we claim to measure? So how well do we understand the measurements that we're taking to have performed? Do we understand the physics connecting the property that we have access to with the fundamental quantity that we're claiming to have determined based on that? Have we managed to put the laboratory into the theory, in Stein's phrase, in order to understand exactly which parts of the theory are relevant? And do we have confidence that the relationship that our theory describes is accurate? And finally, to what extent are the different measurements independent? So I think the independence is crucial in arguing against the possibility that the agreements in the measurements of the parameter values is merely a coincidence. So the independence helps to answer the worry that there might be a different explanation, that they just happen to have the same value by chance. Okay, so I haven't said much about what these parameters actually are, but they're different ways of characterizing the matter density and the features of the early perturbations that lead to structure formation and so on. And I'm not going to go into a lot of detail, but the emphasis that I'm putting is on the overall structure of the argument as being similar in some ways to the argument that Haran gave. So let me reflect for a moment on the shifting status of the FLRW models over the course of the 20th century. So Einstein actually criticized Friedman's paper where he introduced these models. This is a line that thankfully he struck before he sent off the criticism to the journal, where he said physical significance can hardly be ascribed to these solutions. But that was actually a view that he apparently made in person to Lemaitre, and so this was initially when these models were discovered, they were thought as merely mathematical artifacts. Since the 1930s, they were used to give what I'd call a qualitative explanation of Hubble's expansion. So you could see the expansion and you could say, how is it that we can understand the universe is expanding such that we have these sorts of observations? And I think you could give a qualitative explanation, but they were still regarded as physically unrealistic because of the high symmetry that these models had. Now, I think the status of these changed dramatically in around 1965 with the observations of the CMB. And so Charles Misner, for example, was very explicit in effectively saying, we had something that we could treat as just a mathematical idealization before. Now we have to take it seriously because there was it was a long time before they detected any change in temperature from different regions of the CMB, and that indicated that these simple uniform isotropic models were actually very good models, even for the early universe. And so one consequence of this discovery of the isotropy of the CMB was that it spurred a whole industry devoted to trying to understand how the universe could be that symmetric at that early stage. And that led to theories of the early universe that were meant to explain those properties based on an earlier stage of physical evolution. What I'm most interested in is the last stage, where we have a number of inferences that people are making in cosmology that depend essentially on the claim that the universe is well described overall by an FLRW model. So this is a claim that goes beyond just saying that general relativity is effective at cosmological scales. It's a claim that the FLRW models, or perturbed FLRW models specifically, are good representations of the structure of the universe at large scales. And so in particular, for arguments that observations of the redshift to distance relationship for supernova, for the claim that that forces you to introduce a non-zero cosmological constant or dark energy, those arguments depend upon the claim that the large-scale geometry is well approximated by an FLRW model. So we've made a transition from thinking that, first of all, the FLRW models are not even physically reasonable, to thinking that they give a qualitative explanation, to actually relying upon them in an important way in making inferences from observations. And so I think it's crucial, and this is, I think, why cosmologists have started to scrutinize very carefully the case for accepting FLRW models. And in the next part of the talk, I want to look at then the question, how do we discern an FLRW geometry in the phenomenon? And in particular, there's different answers at different scales. So the arguments as to why we should think that the geometry of space and time is well described by an FLRW model at large scales is based on features such as the distributions of galaxies and quasars, the number counts of these objects exhibiting a kind of uniformity. Probably the strongest argument in favor of using the FLRW models is the isotropy of the cosmic microwave background. And that's been very, very well studied. But there's another question, which is, how can we, so at some level, obviously, the universe isn't described by an FLRW model well at small scales. And so the question is, how should we take that into account in thinking about the way that we're measuring cosmological parameters? Is this something that has an impact on the way we're treating these cosmological measurements? So, so I think there's actually kind of two different problems here. I'll mention this one first and then come back to it in a moment. This is from a paper by George Ellis. So imagine that we think that the actual space-time geometry is given by something, I mean, this is just one-dimensional, but it's meant to represent a case where you have the sharp spikes would represent regions where you have high density, such as stars or black holes or any kind of concentrated clumps of matter. And if we think that a galaxy distribution will actually look like large spikes in the region where there's matter and then basically flat in between, the top would give a more accurate description of the density, and so we'd have a metric that would be very inhomogeneous at that scale. And we can then ask a quite general question: how do we think of the relationship between that scale and other scales? So if you think of this as a kind of intermediate scale, maybe this is a galaxy level scale and this is an even larger scale. How do we think of the maps between those scales? And how do we determine what the best fit is at these different scales? Part of the issue is that it's going to be very hard to define a notion of average in a context like general relativity where you don't have obvious structures that you can employ to introduce averages. But the general question is, how do we smooth out these local irregularities and treat the large-scale model as a good approximation to the actual inhomogeneous model? Now there's a separate kind of question, which is, how do the measurements or observational inferences depend on the FLRW geometry? So if we actually think about schematizing the observer and imagine them as located as we are on a planet inside a galaxy scale mass distribution, and we're trying to measure things about the overall Hubble flow, how does the fact that we're in an inhomogeneous mass distribution affect our measurements? So, and how robust are our measurements to the fact that we're not in an exact FLRW geometry? So are the ways we're characterizing these measurements sensitive to the assumptions about the overall geometry, or can we modify them and give a more realistic description of the space-time geometry and still make the claim that we're measuring these cosmological parameters? So I'm going to focus on the last question first. So in very broad brushstrokes, where do the assumptions about the FLRW geometry come in? Typically, if you look at the different cosmological observations, they come in determining cosmological distances. So you're going to have relationships between angular and luminosity distance and redshift, and determining those distances is often, there's a formula that's derived for the FLRW models that you're then relying on in determining those distances. And ultimately then, you're also assuming that there's a description of how light propagates through the FLRW geometry that allows you to characterize the relationship between what you're observing and the object far away. And I'll just mention that if you think about the kinds of observations that are being performed in cosmology, the light beams that you're considering have very different characters. So if you're looking at the observations of a supernova, you're in effect looking at a single, you could think of it as a single ray reaching you from the supernova. But for some other kinds of observations, such as looking at the temperature variations in the CMB, you're actually looking at a large region of space and time. So you're actually considering light that's propagating through a cone, and so it's propagating through space-time in such a way that it will be, you have to think about the description of the light propagating through a region of space and time rather than just, in effect, thinking about it propagating through a ray. And this is, there's papers in the 60s who were the first to consider, this is actually not a paper, it's Jim Gunn refers to, Jim Gunn published a paper in the 60s in which he says that Feynman had given a lecture in '64 asking this question, and Zeldovich has a publication, he's a Soviet cosmologist, how should we describe light propagating through an inhomogeneous universe? And there's actually a very striking contrast between the way that light propagates through something like the top and something like the bottom. So in a Friedman, Lemaitre, Robertson, Walker model, you're describing the intervening spacetime as filled with a perfect fluid. And so the Ricci tensor, so the light propagation is affected by a combination of the Ricci tensor and the Weil tensor. And in this case, because it's a perfect fluid filling the intervening distance, the Ricci tensor is non-zero, and the Weil tensor is 0 throughout the region that the light is propagating. On the other hand, if you imagine, this didn't come out as well, but if you imagine something that's more like a lumpy distribution or clumpy, like a galaxy scale mass distribution, the light is actually propagating through a region where, for most of the way, you can actually say it's propagating through what effectively looks like flat space. Rather than something with a non-zero Ricci tensor, it's going to be a Ricci tensor 0. The Weil tensor can be non-zero if you're going close to the matter and not directly through it. But it's a very different description of the evolution of null geodesics in these two situations. And the question is, does that make a difference, right? So this is, physically, there's a difference in the way that, there's a different situation that we're describing in these two cases. And what's the magnitude of the difference that results from giving a more realistic description of the way, of what light is actually propagating through? And so to approach this question, here's a general way of thinking that you would, for example, say, well, let's try to treat the FLRW model as among a class of more general space-time geometries that we could say are physically motivated, and then ask what happens with light propagation through these more general geometries, and how does that change as we have parameters that vary as we come close to an FLRW geometry. And this is actually, there's a number of people pursuing projects of this sort now. Let me just mention one and explain why it's been proposed and what kinds of problems it might solve. Although, as I said, this is still a very open question, so I don't want to make a strong case that it's obvious that this is the right way to go or anything of that sort. So this is one of the reasons why people have started to think more seriously about light propagation in the sort of local inhomogeneous universe. This is the trouble with the Hubble constant. So these dark gray and gray bars are the values of the Hubble constant determined from supernova observations. All these other values are determined from other types of observations. And very broadly, the contrast is between local measurements of the Hubble constant, which have a higher value. So these are the ones that look at the supernova that are, well, in cosmological terms, local, at low redshift. And the global measurements, including the very high precision measurements from the CMB, have a much lower value. And so, again, there are different ways of trying to resolve this tension, but it's a tension depending on I think it's around 2.5 sigma difference in the values that are determined here. So one possibility that people have explored is, well, perhaps the tension arises because we're actually describing different types of measurements. The local measurements are sensitive to the small-scale inhomogeneities of the local universe. They're also probing the space-time geometry in a different way because these are cases where you're really looking at a light ray coming from a supernova.
These, on the other hand, are looking at very distant objects over a large angle. And so perhaps we should think more carefully about what we're in fact measuring in this case. Rather than thinking that we have a conflicting measurement of one quantity, maybe we're in fact looking at slightly different things. And so again, this is just one concrete proposal of an attempt to assess what happens if you give a more accurate description of light propagation in these models. And this is, so Einstein and Strauss actually first introduced this idea of a Swiss cheese model, where you take a Schwarzschild solution, so you have an overall expanding universe model, and you take out a chunk, and then you put in a Schwarzschild solution, and then you have to match the boundary conditions appropriately. And they were actually originally interested in just whether there'd be any effects of cosmological expansion on solar system scales. But you can do that repeatedly, and imagine that you have a Swiss cheese model now describing multiple sort of concentrated distributions of mass, and then the gray area is still an expanding universe model with a perfect fluid in between. And the paper here by Fleury et al. Does a calculation then where you imagine changing with the parameter the amount of matter that's concentrated in the Schwarzschild type holes as compared to an FLRW model. So in the extreme case, it's just an FLRW model. And on the other extreme, you have the same average density, but it's all concentrated in these specific holes. And they argue then that you actually have quite a striking shift. This is the value of the Hubble constant normalized in a way that's fairly common, and then also the matter density. And they see that there's a shift in the overall measurement of those quantities corresponding to the effects of light propagation. That's quite substantial. So again, the F equals 0 corresponds to a case where you have clumps. The F equals 1 corresponds to normal FLRW. And it's hopeful in the sense that it moves the observations in a way that's more compatible with the limits on those two quantities placed by Planck. So again, my interest in this case is that methodologically, I think it's a very natural thing to start schematizing the observer in a more concrete way, given the level of precision that these measurements have now reached. So they're at the scale where, if you look at actually the error bars here on the measurements of the Hubble constant, they're quite impressive. And so the precision itself is forcing people to be much more careful in assessing what's going on in these measurements. Okay, so let me come back to this second question about modeling, and I think in this case the consequences are even, or the state of discussion is even more unsettled. But again, think of how the large-scale distribution, say a scale here, relates to small-scale inhomogeneities. And if we imagine that we started off with a solution at the first scale, where we actually have a solution of the field equations, and then we smooth out the solution to obtain a solution at a larger scale. And we do so by applying some kind of averaging process to the metric and the stress energy tensor. We can ask if those independent things, the averaged metric and stress energy tensor, are themselves a solution of the Einstein field equations. And the answer is that they're typically not. That one way of putting it is that if you construct the Einstein tensor from the first GAB and TAB, and then smooth, that doesn't commute with smoothing and then finding the Einstein tensor. So, so these will generally not then be a solution of the field equations, and there's often an extra term called the back reaction term that's then introduced, so that you do have something that's actually a solution of the field equations. Now, the suggestion that's controversial is that this back reaction might be important in understanding some of the inferences that people have made from observation. And in particular, recently, this is the observational case for a non-zero lambda that's based on supernovae 1A, so this is what the Nobel was awarded for. So this is based on the redshift to distance relationship for the supernovae, and they make the case that there's an accelerated expansion that's observed, and that to account for that, you have to have a kind of, some kind of matter that contributes to TAB in the appropriate way. That requires negative pressure, and in effect forces you to have a non-zero cosmological constant. Now, the proposal that has come up in relation to this averaging question is that could this possibly be explained by back reaction instead? So we've said that when we go from a local description that captures all of the inhomogeneities accurately, and we smooth to a large-scale description, we have to add in a back reaction term to characterize the dynamics. And the question then is it the case that that term would actually reproduce the observations we see without having a non-zero cosmological constant? So this is a case where I think there's a very open debate right now. And actually one of the contributors is here. So Bob Wald is one of the people who's written a series of articles with Green about this. I think the questions in the debate are first, what form would the back reaction take? So is it the kind of thing that would be an appropriate replacement of a dark energy type contribution? So in other words, is it the kind of thing that would violate the energy conditions? And also, how much does taking back reaction into account affect these observational inferences? So is it the case that this is a small effect, or is it something that would be large enough to actually obviate the need for a cosmological constant? So I think, again, my claim is here limited to the methodological claim that this is the kind of argument that you get into with higher precision cosmology that really reflects Stein's emphasis on looking at measurements very carefully and seeing what's actually being measured and trying to take into account things like the small scale inhomogeneities and how those are modeled. I think this is very much, well, my uninformed take is that this is still an ongoing debate. Well, that's actually something I can just say. It's an ongoing debate. It's not clear exactly how it will be resolved, but I think there's very interesting questions here about exactly how to model the FLRW model, or how to treat the FLRW model as a limit of a kind of larger class of perturbed models. And so I think it's a really interesting set of questions that are going on in this debate, even though the debate is still ongoing. So let me now just wrap up. So I started off with an interest in looking at a kind of Stein-style approach to empirical content, and in particular asking the question, how can we discern the FLRW geometry in phenomena? And there's two themes overall that I've emphasized. First, that theory dependence shouldn't be taken as an obstacle to objective evidence. It's in fact an essential part of the inquiry. So it's not that we should worry about these arguments because they're so heavily theory dependent. On the other hand, we do have to be very careful in critically assessing the theoretical framework. So, and I think we can do that even in a very heavily theory dependent way by scrutinizing the independence of various measurements and also scrutinizing the idealizations that have been employed in describing these measurements and seeing if we actually have a reliable way of determining the cosmological parameters based on observations. So on that note, I will conclude. Thank you.